Oh, okay. Maybe I won't repeat all of this. So it's not the same. Not the same. Okay. So last time we spoke about the unconstrained features model for MSC loss. And the unconstrained features model for the MSC loss is a mathematical model under which neural collapse is to occur. So here's again a reminder of what neural collapse is. So neural collapse is a set of phenomena where the last layer features are converging to the basically to a class mean. So they're collapsing, activation collapse. The class means converge to this special geometric structure, which is called the simplex CTF. The class means converge up to a scalar to the classifiers. And the behavior of the network converges to picking the nearest class center. Now, this paper by Mixon, Partial, and Pi, or P, proposed the unconstrained features model. This is just a reminder, where the unconstrained features model is saying, imagine you have a mean squared error loss, and imagine that you are able to optimize the classifier W, the bias B, and also the features H. So this is a model in which the features are unconstrained because they're not constrained to be the output of a deep network, right? And here you can see one way of writing the MSC loss, right? Now, by the way, I've updated the slides because there are a few mistakes I noticed last time and also after looking at them after last lecture. So make sure you download the latest slides if you're looking at the slides. So one can write neural collapse, the phenomena of neural collapse using this notation of WH and B. And for example, NC2, which says that the classifier converges to a simplex CTF, can be written as WW transpose is an identity minus a once vector over C multiplied by a once vector transpose. And you can write also NC1 plus NC3 through the following equation, and you can provide an explicit form for the bias. Now, in the last lecture, we said that we can take these MSC laws and we can perform gradient descent over it in the limit where the step size goes to 0. And that's usually called gradient flow. And in this limit, one can see that this differential equation is in fact a nonlinear differential equation. And so it's hard to solve. And what Mixon, Partial, and Pi or P did was they said, let's initialize this differential equation near the origin so that this part becomes negligible and the differential equation becomes significantly simpler. And so this is the differential equation you get. And throughout the slides, I call this the simplified dynamics. Simplified dynamics. Now, for this simplified dynamics, you can prove the following theorem. So what this theorem says is that your simplified dynamics is going to converge to a certain linear subspace written here. And last time I drew this picture, which you seem to appreciate or like or understand, where there was this point, which was the point of initialization, where you have the classifier at point 0 and also the features at point 0, right? It's like a tuple in high dimensional space. And then optimization is, going through a certain trajectory until it reaches a point. And what they're saying is that the point that you reach is a point which is the projection of the initialization onto this subspace. So again, I'll repeat this. Your gradient flow, your simplified dynamics converges to this linear subspace. Converges to this linear subspace, and more specifically, it converges to a point which is the projection of your initialization to this subspace. Do these words mean anything to people in the crowd? They do mean something. Okay. Okay. Now, I also remind you that we had this notation of E, which was a norm that we defined, and basically it's just the sum of the Frobenius of H plus W. And we had a reminder of Kronecker products, but you're probably experts on Kronekers by now, so we don't need any reminders. And we looked at the differential equation associated with the bias B, and we managed to find that this was the closed form expression for that differential equation. And that's where we stopped. And that's where we're proceeding today. Okay, so we now turn to the differential equation of the features and the classifiers. So here's H prime and W prime, which are the derivative of the features and the classifiers with time. And you can simply plug in the differential equation that we have and get that H prime is W transpose R and W prime is RH transpose. So that's taken from this slide. You see W prime is RH transpose and H prime is W transpose R, right? So just copy that and put it here. And it's not the same. Oh, yes, it was related to the movement sensor. And what they claim in the work is that this quantity, this tuple, is just a linear function of the tuple of features and classifiers, and that this linear operator is time varying and self-adjoint. So what does all of this mean? So linear, I assume you know what it means. Why is this time varying? Do you see LT is an operator that's operating on a tuple of features and classifiers. And essentially the words time varying mean that the linear operator is changing with time. Why is it changing with time? Does anyone know? Why is the linear operator changing with time? What is changing about this linear operator? What is LT? Is a good question. So LT is the linear operator at time t. It's the operator at time t. So you can think of this LT basically goes from, you know, the tuple of H and I guess W to H prime and W prime, right? So it takes as input the H and the W and produces their time derivatives. Yes, so Neil says that the reason this linear operator depends on time is because the linear operator depends on R of t, and R of t depends on B of t, and B of t depends on time. So essentially the linear operator depends on time. Is this clear or is this not clear to everyone? So In the next slide, I'll explain why this operator is also self-adjoint. Did I answer in a satisfactory manner to what is LT, Karen? Or is the definition of LT still unclear? I guess this is the definition of LT, which is why I use here three lines, right? So you can think of this as literally the definition of LT. Okay, so how does one check if LT is a self-adjoint operator? How do we check if it's self-adjoint? Transpose. Yes, but no. I mean,
Can we?
Yeah, sorry, go ahead.
Can we just take the inner product of LT with,
yes, yes,
other variables?
Exactly. So the usual way in which you check whether something is self-adjoint is you do LT of H and W inner product with some other H, let's call it H wiggle and W wiggle, right? Inner product over this E norm, and you check whether that is equal to what? To H W tuple inner product with LT H wiggle W wiggle. Does this look like something you've ever seen in your life? You have. Okay. So that's literally what's happening here. So I'll go briefly over the steps because it's pretty straightforward. So here you can see LT applied on HW, inner product with H wiggle W wiggle, right? So that's what I had in the previous slide. Now then you can just use the definition of LT. So here I'm plugging by definition of LT, right? And then you can use the definition of this E norm. And so the definition of the E norm is that it's the Frobenius inner product over the first part plus the Frobenius inner product over the second part, right? Now, if you recall, the Frobenius inner product is related to the trace through this relation. Have you seen this relation? Do you know this relation? Is this a trivial relation? Okay. So basically you can write this inner product in the Frobenius space as a trace, and you can write this Frobenius inner product using a trace, right? Now, once you do that, you can actually use the cyclic property of the trace. So let me remind you, the cyclic property of the trace is that trace AB is trace of BA, right? And so by using this property, you can actually take this R and cycle it to the front. And after we cycle it to the front, we go back to from the trace to the Frobenius inner product. So we use this relationship between the Frobenius inner product and the trace. And so here what we're doing is, let's say this is A transpose, and this is B, right? Then the trace of A transpose B, according to this, is equal to A inner product with B. So here you can see A, maybe I should do it like this, A, and here you can see inner product with B. Make sense? Yes. And here you can do the same thing. So let's call this A transpose. Let's call this B. So here you can see B, and here you can see A. Yeah. Is Tristan the only expert on Frobenius inner products and traces, or is this super clear to everyone else? Oh yeah, you should memorize the matrix cookbook. Yes. And then you just take this together into an inner product of two tuples over the E norm, and you just use the definition of LT again to write this as LT H wiggle double wiggle. So in the end, what you get is the inner product of LTHW with H wiggle W wiggle is equal to HW inner product LTH wiggle W wiggle, right? So this proves that we have self-adjointness. Makes sense? Now, why do we care about self-adjointness? What does self-adjointness give us? What's the first thing we do after we know some? Yes, spectral. Wow. Indeed. So spectral theorem tells us that we can look at the eigendecomposition of LT. And so what we're going to do is we're going to calculate the eigenvectors and eigenvalues of these linear operators. And it turns out that all of these LTs are jointly diagonalizable or simultaneously diagonalizable. What does it mean for a set of operators to be jointly diagonalizable? It means that all of them have the same eigenspaces, eigenvectors. That is correct. So you can basically write all of them as LT equal to U, let's say, lambda T times U transpose, right? Right. Now, here you can see the different eigenspaces. So let's go over them. The first eigenspace, it's easier to look at this thing. So the eigenvalue is 0, and the eigenvectors are tuples of HW, which satisfy these properties. So this might be a bit less trivial, I would say. What do these words mean? So first of all, notice that LT is a linear operator that eats a tuple of HW, right? So if it eats a tuple of HW, it means that the eigenvector is going to be a tuple of HW, right? In terms of, dimensions and so on. So this explains why the eigenvector is a tuple of HW. Why do we have a set here? Does anyone know why do we have a set here? Why am I saying eigenvector when in fact we are talking here about a set? How does a set come into the picture of an eigenvector?
Is it because we're working with a tuple instead of just a vector, or?
No. Span of the eigenspace, no. Oh, Jack knows. So Jack says multiplicity. So what does it mean, multiplicity? It means that if you remember, if you have an eigenvalue which is repeated, right, then it has a multiplicity, and then the eigenvector becomes there's more than one eigenvector that spans the eigenspace. Do these words ring a bell from linear algebra? So if you have an eigenvalue which is repeated, then there's more than one eigenvector corresponding to the eigenvalue, right? And all of these eigenvectors are essentially spanning the space corresponding to the eigenvalue. And that's what's happening here. So E3 is the set of all eigenvectors, okay? Lambda 3 is the eigenvalue which has a multiplicity, and dimension is a bad choice of words which should have been multiplicity. So maybe I should use here multiplicity. Does this make sense? So you have a multiplicity of P times C n minus 1, an eigenvalue of 0, and each tuple HW that satisfies these properties would be an eigenvector. I'll show you how to find the eigenvalues, Neo. I will show you how to find them. It's not through the characteristic polynomial, no. So maybe we should also understand what do these things mean. So what does it mean W equal to 0, C times P? What is the interpretation of this zero eigenvalue for the L operator? So if there is a zero eigenvalue, it means that the operator does not change that part of space, right? So it's basically saying that there is a null space of the operator. Yeah, null space. A fixed point of the flow. I'm not sure if I would call it a fixed point. I would call it it's a part of the. I'll actually discuss this. I think. So maybe we can discuss this later. So let me just make sure that this thing is clear. So notice that here there is an equation that says W equal to 0. What does this equation say? It says that the eigenvector, this specific set of eigenvectors, are consisting of matrices which satisfy that the classifier is equal to 0. And this thing says, what does this thing say? If you had to describe this using human words, how would you describe this thing? This equation. This is a bit tricky. Let's see. Who understands? Center ED. What does center ED mean? Oh, centered. Yes. That is correct. So basically, I see Kronecker with the 1 transpose times H transpose is just going to sum within a class all the vectors H. So for example, if H has a block diagonal, a block structure, not block diagonal. So let's say this is H, right? So imagine that here you have all the examples in the first class, here are all the examples in the third, in the fourth, and so on. So if you have I Kronecker 1 transpose multiplied by H transpose equal to 0, it's equivalent to saying that if you average all the columns here, you would get 0. If you average all the columns here, you would get 0, and so on. So let's say this implies 0 class means. Does this make sense? It does. Okay. So does anyone have any thoughts about why did I assign this eigenspace the name within class variability? Okay, no. So let's keep this question in mind for now, and let's talk about the other eigenspaces. So Neo says, Neo is on fire today. Deviation from the eigenspace measures WC variability. If by WC you mean within class variability, then yes. So essentially, if you take a tuple of H and W, and you project onto this eigenspace, then what you are going to be left with is the within class variability of the class means. I guess it's a bit hard to see that, maybe. Maybe it's a bit hard to see that. Okay, let's continue with the second eigenspace. The second eigenspace is, in fact, two different eigenspaces. One of them is has an eigenvalue of plus square root of n. N is the number of examples per class. The second eigenspace has an eigenvalue of minus square root of n. This is why I write plus minus. This is like writing two equations in a single equation, right? We want to be economic with space. Space is limited. So because we have two eigenvalues here, we would have two eigenspaces corresponding to them, the positive eigenspace and the negative eigenspace. So the eigenspace, again, is a set of tuples, H and W, which satisfy certain properties. So what does this property say? This property says that the classifier has a zero global mean, right? Because if you sum its rows, you get zero. So it means that if you sum the rows of the classifiers, right? If you just sum all the classifiers, you get a zeros vector. What does this, what does this equation say? Does anyone remember? What is this equation? Classifiers, yes, so it's self-duality. That is correct. So this is a self-duality, but it's not only self-duality, it's also the fact that the H's all collapse to being equal, right? So it's also activation collapse. Because based on this equation, you can see that all the H's within the class are going to be equal. So this equation encodes the fact that H is equal to W up to a scalar, and the H's are equal within a class. Now, notice that, again, in these eigenspaces, in each one of these eigenspaces, we have a multiplicity. And in this case, the multiplicity is P times C minus 1. Why, by the way, why do we have multiplicities in these eigenspaces? Does anyone know? Like, what's the simple reason for the multiplicities? What does it even mean? You know, how does one even many parameters? Yeah, basically the eigenspace, you can think of it as a set, and the multiplicity, you can think of it as how many, what's the rank, what's the dimension of the set. So for example, in this specific case, right, how many degrees of freedom does this tuple have? So because the W satisfies that, so first of all, because the W's are equal to the H's and the H's have zero within class variability, then the number of degrees of freedom that you have here is just P times C, because it's basically how many entries you have in a classifier. And so if you were to construct a basis for this, you know, for this set, you would have P times C basis vectors. And the reason it's P times C minus 1 is because of this constraint, which takes out 1 degree of freedom. P is the dimension of the features. It's like how long is each feature. Okay, so the last eigenspace that we have is the eigenspace where the eigenvalue is equal to this thing, which is a bit more unpleasant. So it's square root of n multiplied by 1 minus the number of classes times beta as function of t. Beta as function of t was the bias at time t. And in this specific case, the eigenspace, again, there's a positive eigenspace and a negative eigenspace. And in this specific, the eigenspace has the following restriction. So what does this restriction say? What does this restriction say? This thing.
Does it say that W is rank 1?
Yeah, exactly. It says that W is a rank 1 matrix. And this thing says that the H is also a rank 1 matrix. So this whole eigenspace is basically corresponding to the global mean. That's why I call it the global mean eigenspace. And so you can think of it as by taking a certain tuple of H and W and projecting onto this eigenspace, you would essentially get something that corresponds to the global mean. If you don't see the intuition behind the eigenspaces, it doesn't really matter, to be honest. What's important to understand is that we have an operator LT. The operator LT is self-adjoint, therefore we can diagonalize it and we get, a set of eigenvectors and eigenvalues. And the eigenvectors and eigenvalues can in fact be calculated. Calculated in the sense that you can characterize them. Maybe calculated is a bit of a strong word. So let me show you why are these eigenvectors. So what is the dimension P? P is the length of the H's. So let's say HIC is in RP, or capital H is in RP times n examples per class times C classes. In the last eigenspace, H and W are rank 1 matrices. That is correct. Does this answer the questions, Amireza? I have to think more. Okay. Okay. So let me show you how does one calculate the eigen. Why do we care about eigen? The composition of L2 is a beautiful question that we will address soon. I will address that soon. Unless you want me to address it now, I'm willing to deviate from the narrative and address it now, when I think it's okay. I think it helps you to calculate the flow as a weighted sum of spectral projections. That is correct. That is correct. Yes. So let me show you, for example, here I'm showing you the E3, right? So this is this eigenspace, right? So I just copied it here. So how does one check if, if what I claim here is in fact an eigenspace? So an eigenvector should satisfy the relation that LT of H and W, which belong, so assuming H and W are in the set E3, then you should have LTHW is equal to a scalar lambda 3 multiplied by H and a scalar lambda 3 multiplied by W. So this is just the definition of an eigenvector eigenvalue pair, right? And so here you can see that this is in fact the case. So here I'm looking at LT of HW, right? And you can just plug the definition of LT of HW and get that it's W transpose R, RH transpose. So this is just using the definition of the linear operator, which we had a few slides ago. Now, at this point, you can plug in the definition of R. So R was this thing, and I plug it here as well, right? And at this point, you can use the properties that are satisfied because H and W are in E3. So why is this thing equal to 0? So first of all, notice that W transpose times once, or actually this whole thing is 0 just because W is equal to 0, right? W is equal to 0 because we're assuming that H and W are in E3. Make sense? Now, why is the second thing, why is this thing 0? Why is this thing 0? So, oh, sorry. Yeah, it's by the condition in the set, as Gina says. So for example, 1 transpose H transpose is 0 because of the fact that H has 0 class means. And so if H has 0 class means, then if you sum one NC transpose H transpose is just going to sum all the columns in H, right? And so if the class means are 0, then summing all the class means would also give you 0. Do these words make sense? Maybe I should have started with this one. This one's easier. So this one multiplied by H transpose is 0 because of this condition. So that's simple, right? So the bottom line is, as Gina says, by using the fact that H and W are in the set, you can justify the fact that both of these are 0, 0, and therefore you get that this is equal to lambda 3, which was 0, multiplied by H, and lambda 3, which was 0, multiplied by W. So this proves that this is an eigenspace, right? And similarly, you can do this for the other eigenspaces. Do you want me to show why are the other eigenspaces, or should I skip this? I guess it depends on how clear is this or how unclear is this. It's just plug and check. That is correct, Neo. That is correct. So Neo does not want me to go over the other eigenspaces, and we shall accommodate Neo's request and skip them. Okay, so now we're ready to answer Luke's question. So let me just go here. So Luke asked, why is it useful to look at the eigenspaces, eigenvectors, eigenvalues, and so on? So imagine you have a simple linear differential equation, something like dx to dt is equal to a, let's say it's not a simple linear differential equation. You have something like at times x, right? Imagine that someone whispers in your ear and says at is simultaneously diagonalizable. Hard word to say. Diagonalizable. So it means that all of the eigenvectors are going to be fixed and independent of time, and the eigenvalues are going to depend on time. So lambda t here is a diagonal matrix of the eigenvalues, right? So imagine that, so this becomes just u times lambda t times u transpose times x, which should be a small x. Now, imagine I multiply on the left by u transpose. You get u transpose dx to dt is equal to u transpose times u times lambda t times u transpose times x, right? And so at this point, you can define z to be u transpose x, right? And what you get is dz to dt is equal to, so this thing is an identity because of this because of the fact that the eigenvectors are orthogonal. Who knows why are the eigenvectors orthogonal? Trivia question. Why do we know that the eigenvectors are orthogonal? SA, I don't know what SA means. Oh, self-adjoint, yes, that is correct. And so what you get here is lambda t times z. Okay, now why is this? So this shows to you that by moving from the original space of X to this new space of U transpose X, you obtain a set of separable differential equations, one for each eigenspace. Do you see it? Because lambda t now, originally this thing was not diagonal. So you had differential equations which were coupled, right? Whereas in this case, lambda t is diagonal, so you get a differential equation per each eigenvalue, or per each eigenspace, depends how you want to look at it. Does this answer the question, Luke? It does answer the question. Okay, so can we have the case in which u is a function of t? You can have the case, but notice that in all of these eigenspaces, there is no dependence on t. In the eigenvectors, there is dependence in the eigenvalues. So for example, here you can see beta as function of t. So beta, yeah, of course you can. Yeah, you can have a case. Yes. You did solve for the last one last time. That is correct. Karen asked, how did self-adjointness allow us to kill the leftmost factor? So if you have a self-adjoint operator, then the eigenvectors are orthogonal. There's a theorem in algebra. I think it's the spectral theorem, no? Spectral theorem? What's the name? Trivia time. Spectral theorem, yes, that's what I believe. Okay, so just to again emphasize this, notice that this, Neo, are you in my linear algebra class by any chance? Because I was actually showing this video in my linear algebra class about Tony Stark as a motivation for the spectral theorem. I guess there's no way you're in my linear algebra class. Okay. Okay, so yeah. I wish Hollywood made a video for each theorem, right? So you could easily motivate everything. Like time travel is a pretty good motivation for learning about eigenvalues. I didn't watch Transformers actually. I tried watching it so many times and I just fall asleep every time. But I'll try again. I will try again. So just I want to emphasize again that this eigenvalue does not depend on time. This eigenvalue does not depend on time, but this eigenvalue does depend on time, which means that the operator is time dependent, but the eigenvectors are all time independent in the sense that there is no t here. There is no t, right? If there were a t, it would have been time dependent. So at this point, we have this original differential equation, which said h prime w prime is equal to a linear operator time dependent on as function of h and w. And now we decompose LT into its, eigenspaces. So we have here pi1 plus and pi1 minus, because, one of the eigenspaces was positive and one of the eigenspaces was negative. So when I write pi, by the way, what do I mean? Pi is an operator that corresponds to the projection onto the eigenspace, right? It's a projection operator. So you have pi1 plus, pi1 minus, And then you have pi 2 plus and pi 2 minus and pi 3, which is the null space. So if you look at the dynamics, for example, in the pi 3 eigenspace, you can see that because the eigenvalue is 0, then you're not doing any changes in that eigenspace, right? Whatever you had there at initialization would remain the same throughout the iterations of gradient flow. I guess steps of gradient flow. So if an eigenvalue is 0, it means that in that eigenspace, there is no dynamics whatsoever. If you have something like a square root n, it means that there is dynamics. And this eigenvalue, in fact, controls how fast is the dynamics in that eigenspace. So notice that because all of these eigenspaces are orthogonal to each other, you can write a set of differential equations for each eigenspace. So for example, here we can see that in the last eigenspace, the differential equation says h prime w prime, this is the derivative, project it onto the eigenspace pi 3, and then you get that the derivative is 0, right? So the derivative in the eigenspace pi 3 is 0, which means that there is no dynamics in that eigenspace. Another thing you can see is what happens if you take h prime and w prime and you project it onto the second eigenspace. In that case, you get these dynamics. So what's happening here? We're just, I think there's a prime missing here. Is there a prime missing here? No, there's no prime. So basically you take h and w, which is a tuple, and you project it onto the second eigenspace, right? And that gives you the derivative in the second eigenspace. Do this equation make sense? This is just rewriting the original differential equation in each eigenspace separately. And so these are decoupled differential equations. Any questions? Any concerns? No questions, no concerns. Okay. Now, each one of these differential equations can in fact be solved easily. I won't show you how to solve it, but it's very easy. And by solving each one of these differential equations, you get the solution in each one of these eigenspaces as function of time. So let's decompress what's written here. So you, for example, you take h and w at time t. If you project it onto the first eigenspace, pi 1 plus, you get that it's equal to pi 1 plus of h0 and w0 multiplied by a scalar. So notice that this implies that in order to know where is h and w at time t, all you have to do is look at h and w at initialization, project them onto this eigenspace, and scale by some scalar. And similarly for the other eigenspaces. So essentially, you take your initialization, h0 and w0, you project it onto a certain eigenspace like pi 1 minus or pi 2 plus or pi 2 minus and so on. And then you just have a one-dimensional differential equation that you can solve in closed form expression. Does this make sense? How do you determine the scalar? Basically, the scalar is a solution of a simpler differential equation, which is happening in, it's basically a one-dimensional differential equation, because if you're projecting onto the eigenspace, then if you project onto the eigenspace, then you get a very simple differential equation, which is in one dimension. So maybe I can go back here. So in our case, if you have dz to dt lambda t times z, in our case, lambda t would be a vector where you would have lambda 1 plus lambda 1 minus as function of t, lambda 2 plus as function of t, lambda 2 minus as function of t, and lambda 3. So it's just 7 dimensions, right? And z would be also 7-dimensional vectors. You would have z1 all the way to z7, and they're all decoupled, right? So you have d z1 to z7 to dt. So you have 7 equations which are separable, and you can just solve each one independently as a one-dimensional differential equation. So Karen asks, where is the epsilon coming from? Which epsilon?
This is one slide up.
Yeah, so the epsilon is, ignore it, it's a typo, I'm sorry. Typo. Okay, so if you solve each one of the differential equations, you get this thing. Now, oh, it's not 7, by the way, it's 5. I don't know why I said 7. It's 5. It's 5 differential equations. Now, it turns out that each one of these things that I highlighted, only pi 1 is problematic. Yes, we'll get to there. We'll get to what you're saying, Amarissa. So it turns out that all these terms that I highlighted in yellow are less or equal than this quantity. So this is just a finite quantity that depends on the dimensions of the problem. Exponent to the power of 2 over c squared of n, something. Now, the only term that is not bounded is this term. Do you see how this term has exponent to the power of nt? Do you see this? What does this mean? What does this mean? What is the significance of this observation? If it has any significance. Blows up, goes to infinity. That is correct. So this quantity is going to blow up. Now, in the last part of the proof, all you have to do is say that HW, the tuple of features classifiers, is close, so minus this part that is this thing that corresponds to pi 1 plus, right, is at most this quantity multiplied by that thing. So why is this correct? Because, does anyone want to say maybe, why is this correct? So notice that here we have the features and the classifiers at some time. Here we have the features and the classifiers at some time after being projected to the eigenspace pi 1 plus. And here we have the features and the classifiers after you project away that eigenspace. So if you project away that eigenspace, what are you left with? You're left with everything besides that eigenspace. So you're left with these eigenspaces, right? So you're left with these eigenspaces are identity minus pi 1 plus. So as Karen says, this is indeed the complement of pi 1 plus, right? And so we know that each one of these things in yellow are bounded by this quantity, right? And so what this implies is that the distance between HW and HW projected, so this thing is this thing, right? So it's projecting onto the pi1 plus eigenspace, and the distance is bounded by that quantity. Does this make sense? I feel like my explanation is a bit not, maybe not the clearest, but does anyone have any questions? No questions? No questions. Okay, now the only thing that's left to do at this point in order to get the theorem is just take this equation, or inequality rather, and just divide everything by e to the power of minus square root of nt. And that's how you get this equation. Okay. So notice what is the significance of this theorem? The significance is that you're rapidly converging. It's nice that the theorem no longer looks like black magic. That is correct. Yes, it is nice. And what is the significance of this theorem? The significance of the theorem is that it shows that we rapidly converge to the eigenspace pi1 plus, right? But what is the eigenspace pi1 plus? The eigenspace pi1 plus was, let's see if I have it written. Let's just say here, this thing, this is pi1 plus. Pi1 plus. So essentially the fact that you converge rapidly to pi1 plus implies that your features and classifiers are rapidly converging to a situation where the classifiers have zero mean. And so this is zero mean classifiers, and you have self-duality plus activation collapse. Okay. Now, it's actually not an equality here, because here we're talking about a tuple of HW and the bias, whereas in pi1 plus we didn't have the bias, so it's not an equality. Why is the exponent 1 over c squared of n instead of 2? Which exponent? Just exponents. 1 over c squared of n in the theorem. Do you mean this thing? It's possible I'm missing a 2. It is possible. If you suspect, I believe you. It is very possible now. This is slides that are hot from the oven. So this is very possible. Now, last time we discussed how this theorem doesn't actually prove neural collapse, because it does not in fact prove that it proves self-duality, it proves activation collapse, but it does not prove that the classifiers tend to a simplex ETF, right? So in order to prove that the classifiers, this technique used a lot in deep learning research and optimization, like you present a desired limit as an eigenspace or some kind of invariant subspace and then squeeze the complement. No, I don't think so. I don't think so. I don't think so. I haven't seen it in a lot of places, but maybe my knowledge is limited. Okay, so the next thing that we would like to do is prove that we also have convergence of the classifiers and features to a simplex ETF. In order to do that, what Mixen, partial, and pi, or what is the E-norm designed specifically to make LT self-adjoint? Or is there some intuition behind what this norm measures? If it were me, I would actually write this proof in a simpler manner. I wouldn't use this definition of an E-norm. I would just define a linear operator in the form of a matrix and just define, instead of W and H, I would define a long vector that contains W and H. And then I would just use the usual L2 norm. There is no special meaning to this E-norm. There's different ways to, yeah, it's a direct sum, exactly. Yeah. Okay, so the next theorem that we're going to look at is a theorem that proves. So if you remember, we had two dynamics. We had the original dynamics, the original differential equation, and we had the simplified differential equation. So what the previous theorem showed is that the simplified differential equation converges to this subspace, which we call S. What the next theorem shows is that once you're restricted to this subspace, you remain in that subspace for the remainder of the dynamics of the original differential equation. And moreover, in this subspace, you will converge to neural collapse. So in simple words, this theorem says convergence to S, the subspace S, whereas this theorem says we stay in S throughout the dynamics, and if you stay in S, you converge to neural collapse. Okay. Now, in mathematical symbols, what does it mean that we stay in S? What does it mean for S to be an invariant subspace of the original differential equation? It just means that if you have H0, W0, and B0 in the subspace, right, then for all t which is greater or equal than 0, your H, W, and B are also going to be in the subspace. So it's kind of like this, the differential equation preserves this property. And assuming this holds, we'll also show that we converge to neural collapse. So how would you go about proving such a claim? Does anyone have any ideas? How does one prove that a property remains correct throughout the gradient flow steps? Differentiate deviation? No. Project? No. Project.
Can we just show that the velocity vector is contained in that linear space? So
Yes.
it evolves there.
Exactly. So all you have to do is show that the gradient is always in the set. So if the initial point is in the set and the gradient is in the set, then you always remain in the set. Exactly what Tristan said. So here's how you do it. Let me show you an example. So notice that our set is a set of all bias vectors B that satisfy that B is proportional to a once vector. Okay. So what we would like to show is that the derivative of B also satisfies this property. So here's the derivative of the bias. The derivative of the bias is equal to minus Z times a once vector, where Z was a residual. A residual that was defined many slides ago. Now, notice that we can plug the definition of Z, and Z was defined to be this thing, right? Now, at this point, we can just use simple properties of the subspace. So notice that H multiplied by a once vector is equal to 0. Why is H multiplied by a once vector equal to 0? Yeah, zero global mean. So notice that W has 0 global mean and H is equal to W Kronecker with ones. So if you just sum all the entries in H, you're effectively summing everything in W and you're effectively obtaining 0. So if you combine these two equations, you get that H times ones is 0. Here's another thing. We have here 1 NC transpose multiplied by 1. So that's very simple. It's just NC, right? And the last thing is also very simple. So overall, what you get is that B prime is equal to a scalar multiplied by B. But we know that by assumption, B is a once vector. So therefore, you get that this thing is proportional to a once vector, right? So we're essentially using the assumption that, I guess to add to what Tristan said you need to look at the derivative and show that the derivative belongs to the set, but you also need to assume that your current point belongs to the set, right? So if you assume your current point belongs to the set and you prove that your derivative belongs to the set, it means that you will always be in the set. Does anyone have any questions? Any questions? No questions. So let me show you another example. So another property that our set satisfies is that the sum over all the rows is equal to 0, right? So let's try to see if that's also an invariant property. So imagine we look at the average of all the rows in the derivative of W with respect to time, right? So again, we plug in, instead of W prime, we plug in the derivative, which is ZH transpose. Z was just this residual that's written here. And at this point, we can see that this thing is equal to this thing, just using simple Kronecker properties. And this thing is equal to 0, again, by using the assumptions of the set. So which Kronecker properties are we using here? The only Kronecker property you need is to calculate this multiplication, but that's pretty simple. The last thing we're going to do is to show that these properties satisfied. So this is a bit more tricky. So in order to do that, what we're going to do is we're going to calculate H prime, and we're going to calculate W prime, and we're going to show that H prime is equal to 1 over square root of n of W prime Kronecker 1 transpose, okay? So I guess it's a bit tedious, so maybe I should skip this, but basically this is what this slide does and the next slide does. So there is nothing really to it except using the assumptions that your current point is in the set and just using Kronecker products, okay? So I'm just gonna skip this. So at this point, we've seen that the gradient satisfies that it's always in the set S. And so the set S is an invariant set of the dynamics. So that means that H and W always remain in the set. Now, the only thing that's left to do is show that as a result, you get a simplex ETF. You converge to a simplex ETF. So in order to do that, what we're going to do is look at the derivative of W multiplied by W transpose. right? So W multiplied by W transpose derivative with time is equal to this. So this is just a formula for the derivative of multiplication. Now, at this point, we can plug the derivative of W with respect to time. So from one of the previous slides, we know that the derivative of W with respect to time is equal to square root of n multiplied by WT minus WT transpose. Okay, it's one of the slides that I skipped. Now, if you just plug this in, so here's what you get. This thing multiplied by W, so this is W prime multiplied by W. So this is W transpose, right? And similarly for the other quantities, so you have WT here, and you have W prime here, okay? Now, at this point, I'm going to define G to be equal to W transpose, sorry. So G stands for gram. Now, notice that this thing is just G prime by definition of G. And this whole thing can be written as square root of n times G minus G squared. Do you see? Because let's say this quantity multiplied by W is just this G squared, right? Do you see that? G squared appears. Now, why is this significant or interesting? Because if you have here G prime T is equal to square root of ng minus G squared, then what can you say? You can say that, what can you say if this is the case? The variance? It is a variance. So what you can do is just look at the differential equation in terms of the eigenvalues. So imagine you just rotate this differential equation and just look at the eigenvalue part. So instead of G prime, you would get the derivative of the eigenvalue. And instead of G minus G squared, you would get the eigenvalue minus the eigenvalue squared. So again, you rotate the whole dynamics to the eigenvalues. Now, why is this beneficial? Because this system is very simple to solve, right? So why is this system very easy to solve? Because you just equate this to 0 and you get two cases. Either your eigenvalue has to be 0 and then it's 0 forever. So this is this case. Or your eigenvalue is greater than 0, and the only way this becomes equal to 0 is if the eigenvalue is equal to square root of n, right? So this is just a simple dynamical equation in each one of the eigenspaces of the ground. Now, why is this significant? Because what we've managed to show is that all the eigenvalues except the one that is 0 converge to the same value. And that is, in fact, one of the characterizations of a simplex ETF. So if you have a matrix where C minus 1 eigenvalues are equal to some number, and the last one is equal to 0, that matrix is, in fact, a simplex ETF. It's actually important, if I want to be, very precise, it's important to also prove that the eigenvalue, which is 0, corresponds to an eigenvector of 1s, but you can show this. But let's keep it at this so that we don't lose people. So this is the end of the proof, or the attempt of a proof. Does anyone have questions? Could you be more explicit on the link between the simplex ETF? Yeah, so basically, let me switch. So if you remember, one way to show that something is a simplex ETF is to say that WW transpose is equal to is proportional to identity minus 1 transpose over C, right? And so if you look at the eigenvalues of WW transpose, it's equal to some constant or 0. So let's say this is the ith eigenvalue. So from 1 to C minus 1, you have a constant. And for I equal to capital C, you have 0. Why is that correct? Because these are the eigenvalues of this matrix, right? So because this matrix has an identity would have a set of eigenvalues. I guess it's just one. I don't know why I'm writing constant. An identity has, C eigenvalues, which are 1. And by subtracting this rank 1 matrix, you're killing one of the eigenvalues and making it 0, right? So this is an equivalent, instead of saying W is a simplex ETF, you can just say that W has, so lambda I WW transpose is equal to 1 or 0. So this would be from 1 to C minus 1. And null space is the ones vector. Null space is the ones vector. What I mean by that is that W multiplied by 1 transpose is equal to 0. So it would have been more proper to say that, never mind, I don't want to confuse you with the singular value decomposition. I feel like some people don't want singular values because they're not super clear. Does this answer the question, Karen? It does? Okay. Why is only one of the eigenvalues of the solution to the differential equation 0? The reason is that the G was equal to WW transpose, right? At convergence, W, so if W is a simplex ETF, then this would become identity minus 1 transpose over C. And so this would mean that the rank of G is equal to C minus 1. And G is also a matrix of size C times C. Does this answer why is only one of the eigenvalues of the solution to the differential equation 0, Amireza? Or maybe Amireza is referring to this assumption that I haven't specified, which is that you need to assume that you initialize W. So you need to assume that the initialization is of rank C minus 1 or higher. Otherwise, you're correct, Amireza. In that, otherwise you can just initialize W with 0 or something, and then it would be stuck there. Any other questions? No other questions? Okay, so to summarize this part of the lecture, what Mixon, Partial, and P or Pi argue is that neural collapse happens if you have MSE loss, and if you do gradient flow directly on the features and the classifiers, which is why it's called the unconstrained features model, and they show this under the simplified dynamics, right? If you remember, we needed to assume that there is initially these simplified dynamics, which are correct if you're initializing next to the origin. And under those assumptions, you can prove that neural collapse emerges. And the original work that found neural collapse looked at cross entropy loss and looked at SGD on deep networks, which is a bit different, but it's of course nice to see that you can understand when does neural collapse emerge in certain mathematical models. And I think this shows one type of research that people do in deep learning, which is you try and find a phenomenon empirically, and later you find a mathematical theoretical model that tries to recreate the phenomenon and perhaps study it more in depth and maybe find other phenomenons that were, originally unknown. in the experiments. So with that, I would like to move to, I want to briefly review some other works. What do you mean by saying more realistic losses? So in practice, people don't train deep networks with mean squared error loss. They use cross entropy loss. And the reason they, Mixon, Partial, and Pure Pi chose to analyze MSC loss is because analyzing MSC is significantly easier. I assume that's why they chose it. Maybe they have other reasons, but. So I should mention some other works that also proved neural collapse. So some examples. So this is the work that we've discussed. So this is Mixon, Partial, Pure Pi. And this is the theorem that we just discussed. So let me just skip that. Another work that when you pass to the D, easier because of better linearity. When you pass the differential equation. No, it's even more than that. Essentially, the MSC loss is significantly simpler in no matter how what you're trying to prove. MSC loss is significantly simpler than cross entropy, because the cross entropy loss has the softmax in its definition, which is always going to create a nonlinearity in the gradient, in the Hessian, and everything. I'm not sure if that answers the question, though. Okay, so there are other works that try to, that prove that neural collapse occurs in certain settings. So for example, this work by Jianfeng Lu and Stefan Steinerberger. They say we consider the variation problem of cross entropy with n feature vectors on a unit sphere in RD, Duke University. And we prove that if the dimension of the features is greater than n-1, then the global minimum is given by the simplex equiangular tide frame, which justifies neural collapse behavior. So essentially, this is another work that proved that neural collapse emerges, but what they've done was they considered the cross entropy loss instead of the mean squared error loss, and they didn't look at the dynamics. They just proved that the optimization has a global optima. So let me show you what they looked at. So they looked at the cross entropy loss that is hopefully familiar to you by now. And they considered again this unconstrained features model where the features are allowed to be whatever they want and the classifier is optimized. And they assumed for a strange reason that you have only one example per class. So there is no more than one example in the training set of each one of the classes and no bias. And what they've shown is that if you try to minimize the cross entropy loss, subject to the constraint that the classifiers and the features each have an L2 norm equal to 1, then your global minimizer is going to satisfy neural collapse. So essentially, what they're doing is they're showing this for cross entropy loss under these conditions. These are essentially assumptions, and this implies neural collapse. Now, notice that there is no reason there is no real reason, I think, to assume that the features, have a L2 norm equal to 1, right? If you're training a deep network, then you can assume that the classifiers have a bounded L2 norm because your usually training a network with weight decay, right? Which is imposing L2 regularization on the weights. But the features are not really constrained in terms of their norm. So there is no real reason why you would assume that, right? But if you're willing to assume that, then you can actually show that neural collapse is the global minimizer of the cross entropy loss. And there's other works, for example, by Tommaso Poggio, Andy Bambursky, and Xianli Liao from MIT, who also showed that neural collapse emerges. So in their case, they looked at a deep network with mean squared error loss, and they assumed that there is batch normalization layers and weight decay. So these are very different type of assumptions, and they've proven that neural collapse occurs. Now, they haven't looked at the dynamics that leads to neural collapse like Mixon, partial, and pure pi, but they, on the other hand, show that neural collapse happens for deep networks. I won't go into any of these theorems. I'm just trying to show you what other approaches people might have considered. Now, this is an interesting assumption to be making, the batch normalization, because essentially it implies that maybe you won't see neural collapse if you have no batch normalization. And all the networks that were trained in the neural collapse paper, in fact, did have batch normalization and weight decay. So there is another work which is called On the Emergence of Tetrahedral Symmetry in the Final and Penultimate Layers of Neural Network Classifiers. And again, what they're doing is essentially considering, let's see, they're considering the following optimization problem, where again, you have unconstrained features and unconstrained classifiers, and you're minimizing, I believe, the cross entropy loss subject to the following constraints. So they assume that the features are bounded in L2 norm and the classifier is bounded in spectral norm. But again, it's not quite clear. Why would you assume that the classifier has a bounded spectral norm? Or why would you assume that the features are bounded in L2 norm? Does it make sense what I mean when I say, why would you assume something? It's like if you train a network, right? You're training a network to minimize the cross entropy loss, but you're not imposing the spectral norm of the weights to be bounded, right? It might be anything. So if you're trying to prove something, you want to assume as little as possible about things which are not imposed during training. And the final work that I should mention is called When Does Label Smoothing Help? And have there been empirical evidence for these bounds? I mean, you can calculate the spectral norm empirically and see that it's bounded, but there is no reason to believe it might be unbounded, if that makes sense. The fact that something is, everything on the computer is bounded. There's a finite number of bits. You have floating point 32 or 64. So you cannot go to infinity. So the last work that I wanted to mention was an interesting work by Mueller, Kornblythe, and Hinton. And what they did was they, I don't want to go too much into the details of what they did, but essentially as part of their work, they were visualizing the features in the last layer of a network. And what's interesting about that is that retrospectively, after I've shown you the neural collapse work, you can kind of see that in some of their plots, they have tendency towards neural collapse. So for example, you can see here, in this case, you can see how there's 3 classes. This is CIFAR 100, and they picked 3 classes out of CIFAR 100, and they did something like projection onto a low-dimensional subspace to visualize how those 3 classes look in feature space. And what you can see is that there's in fact concentration of the classes around some points, which are the class means, right? Now, they didn't formalize this, and I guess they didn't pay too much attention to this phenomenon, but after you've seen, the neural collapse phenomenon, now you can identify it in measurements that people were doing in the past. Okay. No, LS stands for label smoothing, which is a technique that is used in training deep nets, but I won't go into it. You can think of it as some type of a knob that you can switch on and off when training deep nets. And you can interpret this plot as saying that if you turn the knob on, you get better neural collapse. Okay, so with this, we are ready to move to the next topic. Okay, so the next topic in the course is called Deep Net Spectra. And so what we're going to do is, first of all, a small introduction to the topic. So in the recent years, there was a boomlet, it's called, in studies of spectra, eigenvalues of different quantities in deep learning. And here you can see a collage of various measurements that were made in the literature. So these are different papers that were published mostly in the last 2 years, I would say. And I'm first going to discuss what have these papers found. So here you can see an example of, this is taken from a paper by Yann LeCun from 1998. In that paper, Yann LeCun calculated the eigenvalues of the Hessian of the loss. So what is the Hessian of the loss? So imagine you have a network which has parameters theta, and you have the cross entropy loss, right? The Hessian is the second derivative of the loss with respect to the parameters of the network. So you can think of it as a matrix of size, param times param. And this matrix is a matrix which is, I guess some people would call it curvature matrix. I call it Hessian. Now, you can actually look at the eigenvalues of this matrix. And once you do that, you see an interesting phenomenon. The interesting phenomenon is that most of the eigenvalues are very small, right? But a few of the eigenvalues are larger than the rest. Do you see? Now, since Yann LeCun's measurement in 1998, other people have done similar measurements. For example, Dauphin. Where is the training? Where in the training is it? So this figure is captured at the end of training, That is a wonderful question. Thank you for asking it. So another person who made measurements of the eigenvalues of the Hessian was Dauphin and co-authors in 2014. So what you can see here in each color, so on the x-axis, okay, I should have explained more clearly what is this figure. So this is a histogram of all the eigenvalues. So on the x-axis, you have the eigenvalue magnitude, and on the y-axis, you have the number of eigenvalues that fall in a certain bin. So it's a histogram. Here you can similarly see another type of histogram. So on the x-axis, you can see the eigenvalue magnitude, and on the y-axis, you can see the probability of an eigenvalue. So what's the relation between the count and the probability? The probability is just the number of eigenvalues that fall in a certain bin divided by the total number of eigenvalues. And what you can see, maybe you can see, let me highlight this. So notice how there's a large, this doesn't highlight anything. Let's pick a color that is visible to the naked eye. So here you can see a large number of eigenvalues in green. And then you can see that there is a set of spikes. Do you see the spikes? Yeah. And this is similar to the type of spikes that we've seen in the work of Jan LeCun. Another work that looked at the spectrum of the Hessian was by Sagun, Levon Sagun, in 2017. So in this case, the plot is a bit different. On the y-axis, you have the eigenvalue magnitude, and on the x-axis, you have the order of the largest eigenvalue. So basically, on the rightmost part of the plot, you see the largest eigenvalue, and on the left hand, you see like eigenvalue number 120. So Luke says the probability in the previous plot goes above 1. Yes. So it seems like my interpretation of this being a probability was in fact incorrect. Yes. Yeah, I'm not sure, but whatever this is, it is proportional to the number of eigenvalues that fall in a B. So I can assure you of that. Should we expect the eigenvalue distribution to go to delta function limit if the training loss is 0 and the number of samples goes to infinity? That is a very specific question. Should we expect the eigenvalue distribution to go to a delta function in the limit if the training loss goes to 0 and the number of samples goes to infinity? I don't know why you expect that, Amireza. Maybe you could tell me why do you expect that? Seems like a very specific prediction you have there in mind. Just like, this is a very specific guess, I must say, based on plots. Because that is what people do in information theory. Okay. That is a very specific guess. I guess you'll be able to judge it in the plots I'll show. So what you can see here is that the threshold here, so basically each one of these curves corresponds to an experiment with a different number of classes. So for example, the blue curve has 2 classes, the orange has 5 classes, and so on. And what Sagun and co-authors found is that the largest eigenvalues in these plots, the number of largest eigenvalues is usually equal to the number of classes in the classification problem. So it's almost as if you have an eigenvalue per each class. So in what follows, I'm going to call the majority of the eigenvalues a bulk, and the eigenvalues which are separated from the bulk are going to be called outliers. Outlier eigenvalues. Okay, and you can see in all of these plots there's a bulk and there is a set of outliers. So in 2018, I wrote a paper that shows how you can actually estimate the spectrum of deep networks which have lots of parameters. So imagine you have a deep network like VGG11, which has 28 million parameters. And imagine you would like to calculate its eigenvalues. That is non-trivial, right? How does one calculate eigenvalues of a matrix of size 28 million by 28 million. Luke is laughing at the idea of doing such a ridiculous thing. And that is, of course, the correct response. So it turns out one can estimate the spectrum. And in these plots, you can see the spectrum of the Haitian for the MNIST dataset, the Fashion MNIST dataset, and CIFAR-10. So in this case, you can see on the x-axis the eigenvalue, and on the y-axis it's the density of the spectrum. Density in the sense of like a probability density, but you can think of it as a count if you prefer to think it that way. And what you can see is that in all cases, there's 10 eigenvalues which are separated from the rest of the eigenvalues. What is the intuition behind these eigenvalues? Do we have one? So that's actually the point of this part of the course, to provide you with an explanation for this phenomenon. Is this what you mean, Karen? So at the moment, there is no intuition, but it will be provided, hopefully. So what this plot shows to you is that even in state-of-the-art, I guess, modern architectures like VGG11, which have many, many, many parameters and are trained on real data, you can see that the same type of structure appears in the spectrum, where there is a set of outliers separated from a bulk. And so this is highly non-trivial because the previous examples looked at very simple cases. So for example, in this case, it was an architecture with a few hundred neurons. And so was this case, and so was this case. So it was either toy models or so it was either toy problems or architectures with very few parameters. So Neo says, if you cannot compute the SVD or the eigenvalues, how did you obtain the graph? I will explain that in the following lecture. So it seems like we're out of time. I think I'm supposed to end this lecture on 5:50, but I always go over time. Is that correct? Or is that incorrect?
I think 5:50.
Okay, so I went over time. I apologize for today and every single time I went over time. 5:50.
I'm confused. Wait, isn't it supposed to end at 6?
Oh, it ends at C. Okay.
Like technically.
Okay, I'm
Yeah.
confused. Okay. So we have time. Okay. I thought I was always going 10 minutes over time. I'm not. Okay. Now, what's going to be useful is to do a decomposition of the Haitian into two quantities. The first quantity is going to be called E, and the second quantity is going to be called G. And G is going to be called Fisher Information Matrix to provoke all the information theory experts in the crowd, which we know there are many. By provoke, I mean in a positive sense. Interest maybe would have been, you are the Fisher. I'm not sure what this means. Is this like a cult or something? I am the Fisher. We are all the Fisher. Where have I seen that? So what is this decomposition doing? It's actually very simple. So imagine you're calculating the second derivative of a loss with respect to the parameters of the model. Let's use capital L. Notice that so let me first write the first derivative. So the first derivative of a loss with respect to the parameters can be written as the derivative of the loss with respect to the logits times the derivative of logits with respect to the parameters. So this is also known as chain rule, right? So this is loss, this is loss, this is logits, this is logits, and this is parameters, right? Now, notice that if you're calculating a second derivative, then you need to essentially derive this multiplication, right? And so if you're deriving this quantity, then you get the second derivative of the loss with respect to the logits. So that's, okay, maybe let's assume for simplicity that f is a scalar, just for simplicity, otherwise we get, so if f is a scalar, then this thing is a vector and this thing is a vector, right? Do you agree? Because the loss is a scalar and the logits are a scalar, so this is a scalar. I think I said previously a vector, so I was wrong. Yeah, so this is a scalar, and here you're deriving the logits, which are a scalar with respect to a vector of parameters, so this is a vector, right? Now, imagine if we calculate the second derivative, then we need to derive the gradient. So if I derive this quantity, then I get the second derivative of the loss with respect to f multiplied by, I need to do the inner derivative. The inner derivative is again the derivative of f with respect to theta, right? Multiplied by the derivative of f with respect to theta. And there's a transpose somewhere. Does this make sense? So just to again reiterate, the derivative of the loss with respect to f, I'm calculating the derivative of this quantity, and that gives me the second derivative of the loss with respect to f multiplied by the derivative of f with respect to theta. Okay, or not okay? Yes, okay. Now, the second thing we want to do is we want to derive this quantity with respect to theta and just multiply by that. So what is the derivative of this quantity with respect to theta? It's just the second derivative. So you get d loss to the f times the second derivative of f with respect to theta. Okay. Now, notice that if f was a vector of logits, then in that case, the second derivative of f with respect to theta would have been a complicated, it would have been a four-dimensional tensor. Four-dimensional? No, three-dimensional tensor, right? Because if you're calculating the derivative of a vector f with respect to theta, then you would get a matrix. And then if you're calculating the derivative with respect to theta again, you get a three-dimensional tensor. So all I want to say is that the formulas get a bit more tricky if you're calculating a derivative when f is a vector. And in the case that f is a vector, you can get this formula. Do you see how this formula reduces this thing, reduces to this thing, is if f is one-dimensional, right? So you can see here the second derivative of f with respect to theta, second derivative of f with respect to theta, the derivative of the loss with respect to the logit, the derivative of the loss with respect to the logit, right? The second derivative of the loss with respect to the logits, the second derivative of the loss with respect to the logits, the derivative of f with respect to theta, the derivative of f with respect to theta, derivative of f with respect to theta, the derivative of f with respect to theta. Do you see the correspondence? You do? Okay, so I think with this, I will end the lecture. Thank you very much for joining, and I'm here for questions.
I have a question about about homework 5. So there was like a part of the question that's not for handed in. So once you've generated the graph and everything, yeah. I was just wondering if I was wondering if I could ask you about that one,
Yeah, sure.
just to just so I understand.
Did the deadline, by the way, pass or it hasn't passed yet?
Sorry,
Did the deadline
I think
pass?
it's tomorrow.
Oh, okay. It doesn't matter though. I was wondering. Yeah.
Okay, I'm gonna share my screen. I'll let you. If you could let me share my screen, I'll show you the.
Yeah.
graph.
Do you want me to stop the recording, or do you want us to record your screen as well?
Oh, I don't mind.
Okay.
Just watch it be like completely wrong.
Okay, so you
Okay.
can share now.
Oh, I cannot share screen when you are.
Oh, right. Stop share. Okay.
Thank you. Okay, I'm gonna share, and let me open. 1 second. Here we go. Can you see it?
I can see it, yeah.
Yeah. So the I don't know how to read this. Actually, I'm the axes are missing.
Yeah.
So I don't really know how to interpret this. So I see that how the margins are being more concentrated and they're being
Yeah.
they're bigger and bigger. So, and then I don't understand what does the horizontal, because I don't understand the histogram function. The horizontal axis where it's labeled from -10 to 40. Yeah, that's the part where I was a bit confused. It
So-
makes sense because you're converging to some max margin where you're maximizing the margin and things are becoming more concentrated.
So first of all, let's make sure we understand the plot. So on the x-axis, you have different values of margin, and on the y-axis, you have essentially a count or a probability.
So I
And so you're essentially plotting the distribution of the margins.
I see.
And what you can see is indeed a concentration. So it becomes closer and closer, all the margins. Now, the reason that happens is related to the fact, do you remember how Gina said maybe a couple of lectures ago that under neural collapse, all the margins become equal?
I see.
Because if you have neural collapse, then imagine you have a two-class classification problem, then all the points collapse to being equal, right?
Right. They concentrate toward like a.
Yeah.
I don't know how to describe it. Yeah.
And if they concentrate, it means that all the margins become equal to each other.
Right, or extremely close.
Right. And so this is what this figure shows.
Nice. But is there a problem? Because now if I read it that way, then the margins are not really increasing.
Right. That is a bit subtle. The reason they're not increasing is because the training of the network is done under a weight decay penalty. So the weight decay, do you remember what weight decay is?
I don't quite remember.
So weight decay is basically you're minimizing the cross entropy of the loss as function of parameters theta plus the L2 norm of theta squared. Oops.
Oh, right. They want to control they don't want the weights to become too big for some reason.
Exactly. And so essentially what this does is it restricts your network from creating margins that diverge to infinity. In order to create things that diverge to infinity, you would need the parameters to diverge to infinity. I
see. I see. So basically, if I want to make it increase, I can just turn off the weight decay and then it will just.
I think in that, I didn't try to do that, but I don't think that would give you what you think. Or maybe you should try, I don't know.
Yeah, sounds good.
I think that turning off the weight decay might have a bit of a non-trivial effect, but I'm not sure.
Sounds good. I will certainly give it a shot. I mean,
Yeah,
it takes.
if you do that, let me know. It'd be interesting. Yeah, send me a picture.
I'll send you a picture after that. I also have another very dumb question. In homework 5, where the task 2 asks you to tweak the learning rate, and then I tweaked it where I think it's supposed to be tweaked. Like you tweak it when at the right time at every epoch iteration, right? When the epoch is at the right epoch, you tweak it. But then there was like a commented line that says task 2 that was like under the definition of optimizer. So
Right.
I don't know what to do with that.
Right.
In the sense that it
did you
work.
try and so I think I said in the homework that you should try and look at the lecture on optimization, right? Did I say that or did I forget to say it? Yeah, hint lecture on optimization. So if you go to the lecture on optimization, I can send you a link. Here's the link. If you look at the slides there, you would be able to identify a specific slide that shows how to do how to decrease the learning rate.
Oh, I see. I think I just went to Stack Exchange and did some very unorthodox things to the code, but I will look at that. Thank you.
So just one thing, I saw that someone wrote on Piazza that they were dividing LR by 10. So that wouldn't do anything.
Yeah, actually, I asked that question. Yeah,
yeah.
I was confused about this as well.
Yeah, so if you divide the scalar by something, it doesn't do anything, because if you have a scalar in Python and you just change the scalar, it doesn't affect the optimizer.
Okay.
Because the optimizer doesn't have a pointer to that scalar.
Okay. Okay.
So what you need to do is you need to create something called a learning rate scheduler that we saw in this lecture on optimization.
What I did was I went to the group parameters and I just changed each one of them like one by one. I think there are like a million different group parameters. You just say for G in group parameter, G of learning rate equal to G of learning rate times like 1/10.
Yeah.
This is like the one I got from Stack Exchange where people just brute force.
Right, so you can do that, but it's much simpler than that. It's just like 2 lines of code.
Oh, cool.
One line is you define the learning rate scheduler, and another line is you need to do a learning rate scheduler step. If you look at the slide number 15 and 16 in the link I sent, you'll be able to see how to do it very simply. But what you're saying, Neo, does make sense. I mean, you can do that as well. It's just that it's slightly non-elegant, let's put it that way.
I see. Yeah, and it's also not good coding practice because you don't want to interfere directly with the parameters.
But this is MAT 1510. It's not CS 1510, so you can have bad coding practices.
Sounds good. Yeah, so I guess we're just expecting the concentration of these things because of neural collapse, and then because the weight decay, you may not be able to see but then I'll send you a picture once I play around with the weight decay.
Yeah, thank you.
Crazy stuff happen. Okay.
Yeah.
Sounds good. I also have a question about a question. So I was wondering if I could come to Officer and ask you a question about, so I was trying to read a paper where they somehow turn the optimization problem into a language that I completely do not understand, which is like signed measures and whatever. I'm trying to wrap my head around it, but I might come to ask you.
Is this the paper by
Optimization God?
Right. Yeah. Okay. Yeah. Okay. Yeah, you can of course come to the officer, but I don't promise I'll be able to assist with that part. but I can definitely try. Did you look at their blog, by the way? I think the blog is supposed to be nice and accessible.
Yeah, I think the blog posts are like after the publication of this paper or something. Like there's not